Could we get that reaction to occur?
Yeah.
Yeah, that reaction can possibly occur. That does occur, even though it's non-spontaneous. How do we end up getting it to occur? We have to add energy into it. How does that change our energy diagram?
It's endothermic? Is that what you mean instead of exothermic?
Yeah, this one's endothermic, yeah.
Well, you have to put in energy first.
So we put energy in, yes. How does that change the energy diagram?
Is it inverse?
You cross something up.
It doesn't change the energy diagram. The energy diagram stays the same. Okay. We're still saying that our reactant energy, which is ultimately dependent on our bond energy, is the same. This reaction is non-spontaneous, and we can get it to occur by increasing the general motion of our reactants so that there is technically an imbalance, and that's how we could get the reaction to go forwards. But we don't change the energy diagram. The energy diagram always stays in this format, okay? Which is kind of odd, but almost sensical as well, because if we could start fluctuating that with temperature, then it becomes even more confusing than it is. What we're looking at when we look at an energy diagram is the raw bond energy, the energy held within each of those bonds, the entropy, all that fun stuff. We don't look at temperature effects within that. So if we want that reaction to occur, we can get it to occur by increasing the energy of our reactants. That doesn't change our energy diagram. It's still an endothermic reaction. Okay? Still technically non-spontaneous. When we shift into biochemistry, one of the things that I was pushing is that we're always getting spontaneous reactions. And I'm not positive on that one, so that was definitely a huge overstatement on that. But if we have a reaction that is not favored, say in this case, what can biology go through and do? Okay, well, catalyzing it, sure, will affect. Now I'm going to need more space to draw. So if we went through and said we wanted this product, and we look at this reactant, okay, that's supposed to be endothermic. Hopefully it's close enough you guys get my drift. It is still technically endothermic. Okay. When we look at just that reaction, we say that's endothermic, that's not like going to happen. And we can use enzymes, which is all fine and well, but what is the enzyme going to do? Lowers the activation barrier. And we might add a couple extra humps in there. That's still an endothermic reaction. Okay. How else could we get that reaction to occur? Could put in energy, but then our temperature drops, and that could be a potentially questionable thing to do within a biology. Every time we decide to run a reaction, our temperature drops 5 degrees. Okay, that's going to have a massive effect on every other reaction occurring within the body.
You have a more like substrate?
My argument is that what biology ends up doing is saying, well, fine, I want that product. And yes, we may be looking at that as a reactant, but instead what I'm going to say is that's something else. And that I'm going to get that reactant from another reaction. Now when we look at the net result on going, sorry, I'm drawing horribly right now, from our initial state to our final state, what's the net result? It's exothermic. So we can supply enough energy from a different reaction to help kind of propagate that process along. Okay? And so that's what I was referring to when we're talking about how we can get these reactions to push. Okay? When we look at an individual system in organic chemistry, we were typically thinking about one reaction. Biology says, okay, there's that one reaction, and that's not a very favorable reaction, but I still want it to occur. I'm going to string it together with 6 other things. And those 6 other things may end up changing, and we may not end up going through that reactant state. We might be shifting through other cases. Okay? So biology finds a different route than we would typically assume. Okay? For instance, if we were going to go through, whoops, that was the wrong slide. When we looked at that ADP to ATP, okay, what did we say had to happen there? We had to add energy into this system. So energy is a reactant. We're looking at this as an endothermic reaction, yet it still occurs. How does it occur? Okay, it occurs by stringing together a couple other reactions, the electron transport chain, to provide that energy to get a different way to force those two things to occur, or those two bonds, or that bond to form. Okay? So we end up tweaking and adjusting our overall perspective. Say that one reaction doesn't work, so let's find an entirely different path. And it may take 6 or 7 other steps, but the amazing thing about biochemistry is that what happens to the efficiency of nearly all of our reactions? Pretty astronomically high. Okay? It's one of the things that biochemistry has a huge advantage over organic chemistry, because in organic chemistry we get a yield at the end for, say, a large molecule. If we get a yield that's in like the 10% range, it's actually a pretty phenomenal synthesis, and you get massive publications in Nature and Science, and you go, oh my gosh, I can't believe you were able to make that. Whereas if you look at the biochemical pathway, their efficiency is something like 99%. Okay? And that's because biologically we can control a lot of those issues along the lines of energetics with enzymes. We end up using astronomically high concentrations in biochemistry. How do we get those astronomically high concentrations? Okay, within cells. So we as humans still can't mimic this. How do we get astronomically high concentrations? What is a concentration?
In a small area.
The amount of, there we go, way to initiate it, the amount of substance per volume. How does biology get massive concentrations? Small space. We take 2 molecules and we confine them to a massively tiny space. We may only have 2 molecules, but the effective concentration at that point is astronomically high. We can't do that, okay, as organic chemists. We end up with very dilute solutions. Okay? But biology has built ways, cells have built ways to keep these things kind of trapped and near each other to force that reaction to occur. Okay? So why could this become important when we look at rates? Well, okay, those of you from 152, rate equals, okay, I can't yell at you. Come on. I know a couple of you had 152 with me. Rate equals, I can kind of accept coefficient. The rate constant, natural log. I don't know where you're getting natural log from. Right idea. And it's not products. Typically it has nothing to do with products. When we're looking at the rate of a reaction occurring, okay, do I care what the product is necessarily? No, that doesn't impact the speed of the reaction. The speed of the reaction is I take 2 things, put them together, and make another thing, another sequence of things. The important part is the 2 things that I start with. It's times the concentration of your reactants. Okay, you can bring in products, but let's kind of avoid that for the moment because that makes the mathematics a whole crap ton more difficult. Okay. When we look at the rate for an individual reaction, okay, it's rate constant times concentration of the reactants. Which of those 2 terms can we change? Can we change the rate constant? No, because it's a constant. So if we try and compare a reaction that we run in some test tube versus what biology is doing at the same time, the rate constant is the same for both of our experiments. The only thing that changes is the reactant concentration. And if biology can make that reactant concentration astronomically high, what happens to the rate? The rate goes much, much faster. Okay? So we are playing with a lot of the dynamics in both energy, looking at the raw differences between our reactant and product energies, but then also at those rates. Okay? And a lot of biochemistry is evaluating those differences to a certain extent. Okay. Other cases, depending on how far into the rabbit hole you want to go, you look at the mathematics, or you pull back and you look at structures, you look at how the shapes overall change, and you try and qualitatively interpret it as opposed to putting numbers into it. Okay. For this course, we will be primarily qualitative because I hate numbers. And I don't hate biology. I know I keep overselling that, but biology is cool. I just can't study it. Okay. So while I was putting together these thoughts or these slides, started thinking about philosophical thoughts for the day. Okay, and I was thinking, why did we choose minimal reactivity? Why did cells choose smaller reactions, okay, as opposed to let's just fight for energy. As soon as I've got energy, now I can go do stuff. Okay? If I don't have energy, I don't do anything. So we're shifting ultimately from this animate to an inanimate object. Why did life decide to develop that we always want this energy and we're going to store and hold on to that and maintain kind of a constant pattern of life as opposed to, whoop, I'm alive, now I'm dead. I'm alive, now I'm dead. Okay? Why do we kind of shift directly along those lines? Okay, some of you may have recognized that. Kind of what I'm comparing here is from Doctor Who. You're looking at what are referred to as the weeping angels that are only in existence when no one's watching them. As soon as you watch them, they freeze. Okay, so it's kind of the reverse thought of what I was thinking about here. Okay. Why is that? I have no idea. That's why it's a philosophical question. Okay. But it's just kind of an interesting thought on how we ended up building life and why did we kind of string these things together. Because we could go through with really extreme reactions. Like if we look at our Grignard reactions, those reactions happen very quickly, very swiftly because we have very high energy states. Why in biochemistry did we kind of hit this kind of middle ground where we don't have these very high energy states? We could go through with too volatile, but that's only volatile because we're used to going through that kind of middle ground. Okay. We could look at easier, potentially more efficient. I'm not positive either way. Just it seems kind of an odd process. Okay.
Obviously, it maintains homeostasis, right?
But why does it maintain that homeostasis? Okay, so that's the real question behind, I think, a lot of biochemistry is, well, why does it do that? Okay, we have developed to maintain homeostasis. But why does it need homeostasis? Why couldn't I just say, okay, now that I have energy, I'm going to go do whatever I want. Whoop, I ran out of energy, now I'm dead.
Because you can't evolve from that. Like,
Why not?
because evolution takes a long time,
Evolution
and if
takes
it's
a long
unstable,
time.
it'll collapse.
But you're saying that energy source isn't constantly available, particularly at the earlier stages of life as we're predicting? I mean, one of the arguments is we have massive amounts of ultraviolet light, massive thermal fluctuations, okay, in our developing planet. Why is that reversible process something that's strictly necessary?
I mean, to maintain a human body, you have to have a certain amount of organization
That's
relative
again
to the outside.
starting at the end and working backwards. I'm saying if we start at the beginning, why does it need to build that direction?
To distinguish itself from the rest of matter.
So the rest of matter becomes alive and dead at the same time?
It is entropic. I mean, it goes
It does
down.
fluctuate, yeah. But so does life. I mean, we do end up pushing eventually towards CO2 and water.
Eventually, sure. But I mean, there is that period of time where there's more organization, and it is somewhat homeostatic and stable. So.
Why did life have to evolve that, though?
Because those are the products, or those are the reactants that were available. If it were different reactants, we would have evolved a completely different way.
I don't know. But like I said, it was just my philosophical thought. I don't actually have any answers for this. Just thought it was an interesting idea. Okay. So one thing for sure we should be able to go back to is kind of the strict science. And we talked about this with our intra and intermolecular forces, the relationship between these. All right? And we could go through and look at individual reactions, and we should be able to compare and evaluate different bonds and the possible interactions that can come out of them. Okay? Where the textbook really pushes this is looking at water and why water is such a fantastic solvent. We'll look at that in a little bit. Okay? So with this, if we look at most life, where do the bonds exist when we're looking at life? Ionic, polar covalent, covalent. Okay. Probably sitting in this polar covalent to ionic range. Why? We get kind of a reactivity coming out of it. We can get different interactions. If everything was covalent, is there a reason for anything to interact? No, we get very weak attractive forces between individual molecules. So if we looked at life being purely covalent bonds, we wouldn't expect them to ever reach an energy state high enough that they would want to interact with something else. Right? Yes, life is going to be dependent on a fluctuation between all of these. But you'll notice that when we start talking about how things interact or change, we typically start to reference a lot of these polar covalent type bonds. For instance, proteins. Okay, I know this is a jump up, but maybe you guys remember. How do proteins get built? What makes up a protein? Amino acids. How do amino acids link to each other to make a protein? You might be going through a phosphodiester in the strictest sense, but let's go simpler than that. It's a condensation reaction forming a peptide bond. Okay, that peptide bond is also known as speaking close. It's not quite an ester. It's an amide. Okay, so if we looked at an amide, we've got the carbonyl with the nitrogen. There's our R groups going out either direction. The linkage between our amino acids is sitting in here. Okay, why is that important? How was that linkage made? If we look at the reverse, we take the nitrogen, also known as what functional group? An amine. And then we have our carbonyl, which is a little bit trickier to deal with. But in the case of our amino acids, what functional group are we getting out of that one? The carboxylic acid. So when we link together, and yes, we'll talk about this in more detail in chapter 3, we're linking the acid with the amine. Why can we build that connection? What's that? Yeah. Those are polar covalent bonds. The nitrogen being much more electronegative than the hydrogens attached to it pulls the electron density away and it becomes partially negative. The carbon attached to two oxygens has lost a lot of electron density and it becomes partially positive. So what we're looking at is two polar covalent bonds that generate dipoles. Those dipoles we can take advantage of as an attractive force that brings those molecules near each other until eventually what can happen? We can make and break bonds and make new polar covalent bonds, okay, linking the amino acids. So really what we're pushing is a balance in between our polar covalent bonds in one state versus in another state. And biochemistry takes advantage of that, builds amino acid, or builds other proteins or RNA or DNA, or not DNA, sorry, RNA or proteins to help facilitate that bond forming. Okay. How are those bonds initially formed? You're probably looking at just a soup of random chemicals that hopefully came together at the right instant to form that. Okay. So we're really concerned about the balances between those. One of the primary things that we're going to look at, particularly in chapter 4, is a lot about intermolecular forces and the interplay of those forces and how they contribute to the overall structure of the things that we find in biochemistry. Proteins, DNA, RNA. Okay? So, why is water special? Actually, before I hit that next slide. But it's taking some time. Because it broke. It's still broken. Okay. Why is water special? Now I wanted to go back to it anyway.
Skip to it, the hydrogen bonding.
Okay, we've got oxygen with two hydrogens. What types of bonds do we have in that? Polar covalent. Those generate what types of forces? Dipole-dipole. Once we have that dipole-dipole, we can now evaluate, do we have hydrogen bonding? Yep. So water is really special because we have this very strong intermolecular force that can start to attract other molecules within it, or keep other molecules within it. That means we can generate solvent spheres almost like a protein itself, trapping these individual molecules near each other. Once they're trapped near each other, what can happen? Now we can get chemical reactions. Okay? So having the polarity of water can really help to kind of bring these other molecules near each other, okay? Which could be a reason why we don't see higher energy states. Because if we use something like a Grignard reagent, very high energy carbon, what happens to it in water?
Oh, no reaction.
There's absolutely a reaction. It's a very violent reaction. It's an acid-base reaction that does what to the carbon? Turning it into a carbon-hydrogen bond, and we've lost all of that chemistry. All of that energy has now been shifted into something of very, very low energy. We can't control that, or we'd have to separate our high energy states from our very low energy states and only allow them to interact at perfect times. If we have intermediate energies, we can now maintain those kind of intermediate high energy states to a point where I can then shift them in balance with something else. Okay, so there could be an argument there for why we want to maintain life in kind of this lower energy state, not getting all the way up into the ionic system. Okay. Are there ionic interactions in life? Yes. Are they ionic when we're looking at carbons? No. Okay, why? That's a really, really high energy state. Carbon doesn't want to hold on to those electrons, okay? Whereas nitrogen and oxygen, being more electronegative, can hold them. Okay? So, water. Polar covalent bonds generating hydrogen bonding. So we get a large partial charge, both positive and negative. That can help to kind of bring in other molecules to get them all into an environment where they can interact. Okay, so water is an awesome solvent in that case. We can bring these things together to allow them to push forwards. Okay, it's also relatively small. Why would size matter? Yeah, it can get around individual solutes to help facilitate their motion. It doesn't really get in the way. So it's polar enough to bring in things, but then not so big that it gets in the way and prevents reactions from occurring. Okay? And then we can also look at kind of a symmetry of water. Water's kind of neat in that response because we could go through and look at other large partial charges. HF. That generates a very large partial charge. Okay. We actually push that to being an acid. Yes, a weak acid, but a stronger acid than water. Okay. Also, very small size. But when we look at the symmetries of this, particularly when it comes back to hydrogen bonding, we don't have as much symmetry. Okay. Well, what do I mean by that symmetry? Because you might make the argument that this has even more symmetry than water. What we're concerned about with that symmetry in hydrogen bonding is evaluating this definition between hydrogen bond donor and hydrogen bond acceptor. Okay, well, what do I mean by that? What is a hydrogen bond donor? Or a hydrogen bond acceptor, I'll take either.
Acid-base?
We can look at acid-base reactions. Acid-base reactions would be the absolute extreme. We want to step away from that because, again, that's putting it at too high of an energy state. We're looking at interactions, not intramolecular. So we're not looking at strict bond changing. Again, you're looking at too much change. Okay, what we're trying to decide, let's take a look at it this way. Let's put HF in the middle just because it's nice and easy to work with. Let's draw in a couple other molecules here. Yes, it's coming back to intermolecular forces. orange is a horrible color to pick. Let me try that again. Let's try purple. See if that, oh, it just hadn't drawn it yet. 1 and 2. Okay. In reference to the red HF in the middle, okay, we want to evaluate those intermolecular forces of 1 and 2. What is HF supplying in the first interaction? Hydrogen. Okay. So if we were going to think about HF, in case number 1, what did HF supply? It was the hydrogen bond donor. It's supplying the hydrogen. If we look at HF in case 2, what did it do? It accepted the hydrogen. So we're looking at a hydrogen bond acceptor. So when we divide up hydrogen bonding, there ends up being 2 classes. We look at the part that's actually sharing the hydrogen. So that's our hydrogen bond donor. And then we can also look at the hydrogen bond acceptor. All right, let's try and dance away from the hydrogen bond or the hydrogen aspect of this. What is the hydrogen bond acceptor doing? Sharing our electrons. For those of you that haven't seen this notation before, I abbreviate electrons as E minus. Okay? So if we go back and now erase all of those interactions and just look at HF, how many hydrogen bond donating capabilities does HF have? 1. How many hydrogen bond accepting capabilities? 3, because we go based on a pair. Okay, we won't look at individual electrons. Why not look at individual electrons?
Free radicals are bad.
Yeah, we could make a free radicals are bad argument. Okay, let's push that interaction to its strongest circumstance. What happens? We would form a bond. How do we form a bond? We need a sharing of electrons. What atom is sharing the electrons? Fluorine or hydrogen? Fluorine. We're looking at a pair of electrons being shared. Okay? So HF is nice because we do get some hydrogen bond donating, but we only have 1 of those. In fluoride, we'd have 3 pairs of electrons being shared. What happens if we jump over oxygen for the moment? Look at our other hydrogen bonding solvent. Could look at ammonia. Ammonia, very similar to water. We've at least reduced the reactivity. It's now no longer this wicked strong acid like we would get in HF. So that's kind of a good deal. Right? But what happens with our hydrogen bonding? Do we get... What's that?
Goes up.
Kind of. In all hydrogen bonding, we get 4 possible interactions. So we can't quite say it goes up. What are you referring to, though?
More hydrogen bonds.
Our hydrogen bond donor becomes 3, and our hydrogen bond acceptor becomes 1. So we end up doing the inverse of HF. So we get kind of the opposite. What happens if we shifted to water now? Those of you that can draw faster or think faster than I've been drawing, what ends up happening is we get asymmetry in our sharing of hydrogens versus our sharing of electrons. Ends up getting 2 and 2. Okay. That symmetry and balance is something that is quite possibly one of the reasons why, when we look at the freezing of water, what happens to its density? It goes down. Okay, which is really, really important for life, because if we think about the fish in the ocean, okay, what happens if that wasn't the case? The bottom of the water freezes, and it freezes upwards all the way to the top. We now have our trapped fish, nicely preserved for when the summer comes around and thaws them, but we end up minimizing the amount of life that can occur in the ocean because we end up removing it. Okay, or removing that possibility for motion. So hydrogen bonding is kind of cool for that respect, and water's very special for that. Why exactly does that density shift? Your textbook definitely doesn't evaluate it. They kind of speculate with your hydrogen bonding theory, which seems kind of reasonable. Okay? When we liquefy water, okay, why does the density increase?
Because they don't have to be arranged in a particular order like they do.
Each of the water molecules can now potentially move, and we have the potential of actually shortening that hydrogen bonding interaction. Okay? They can actually get closer to each other and prevent that symmetry. If they get closer, we end up strengthening those interactions. We probably see some more acid-base characteristics and other things along those lines. Okay? So water's kind of neat for those purposes. Questions about water? I know that was exciting. Full 15 minutes on water. Okay? Can't all be weeping angels. The other name, Carlos already mentioned this, for a donor and acceptor when we push it to the extreme. What was that? I would step away from nucleophile and electrophile, because what atoms are being involved in nucleophile, electrophile? Not hydrogen, ultimately. Typically, we look at carbon with our nucleophile electrophiles. Okay? So what really are we looking at here? Our Bronsted-Lowry acid-base definitions. Okay? So water has that ability to transfer those hydrogens around. When you move into proteins, proteins will end up taking advantage of that hydrogen bonding effect as well and transfer hydrogens onto and off of structures. Not at will, but very close to it. Kind of neat. So if we're going to push into acid-base characteristics, that means we have to have some understanding of what's happening with our acids and bases. Okay? So your Bronsted-Lowry definition, we're looking at the exchange of protons. Your Bronsted-Lowry acid is a proton donor, or a hydrogen ion, and a Bronsted-Lowry base is a proton acceptor. We could look at the electrophile nucleophiles. Okay? Those are looking at the balance of electrons. So if you looked at, say, HCl and how it interacted with water, we could define that interaction as a Bronsted-Lowry acid-base reaction. But just as easily, we could define that as a Lewis acid-base reaction, because we're looking at the transfer of electrons. Okay? So we will tend to oscillate back and forth between these definitions, both in organic chemistry, and I'm going to try my best to bring them in as much as I can into biochem, because I think it's important. Okay? So if we look at some individual reactions here, a generic acid, HA, dissociating into its two components, or we could look at that acid being dissolved in water and dissociating into H3O plus and A minus. Okay? We're getting the same net result in each case. We're just introducing water, which kind of acts as a mediary, okay? Just to make it look a little bit nicer, if you wanted to say nicer. How could we decide that HA was stronger or weaker than another? If it completely dissociates. So what we end up saying is that instead of this being an equilibrium reaction, so we don't see that arrow, the double arrow anymore, we see it just go one way. Okay? Well, that's nice. How do you decide that? I give you two containers up here, clear liquids. How do you know which one's the strong acid? Okay. We've got some very awful ideas on how we could potentially determine which one's the stronger acid by drinking it and seeing if you are in severe pain. Let's just push the pain object. Okay. You could try and stick your hand in it and see if you see a reaction that way. Those are potential ways to do it, but not the nicest. Okay. One of the other good options is we could look at pH. Okay. What does pH measure? It's ultimately the concentration of hydrogen ions, which is partially dependent on whether the acid was strong or not, but it could also be dependent on just how much of that acid you put in there. Okay. We could put in a single molecule of HCl into a container of water, or we could just take a container of acetic acid. Okay. The acetic acid is going to have a much higher concentration of H plus than the HCl molecule. So it's not a direct relationship, but it can get us an idea, okay, or a ballpark. Okay. So there is something else going on. It's the amount of dissociation. Can we quantify the amount of dissociation? Yeah, how do we do that? We're looking at our equilibrium constants. Okay. The balance of our products and our reactants and how these end up shifting across. Okay. So the extent to which our acid dissociates, we can look at our equilibrium constant. This works for all reactions because we could look at these as any balance of products and reactants. Okay? In biochemistry, we tend to shift back to primarily looking at our Kas. Why acid chemistry? For some reason it's easier than base chemistry. Why acid or base chemistry? It's the easiest reaction to work with. Okay? So, general review of your equilibrium. For an individual reaction, I would say there's kind of two ways that you could compare the meanings of equilibrium. Okay? The one that we already kind of mentioned, it's the balance of our products and our reactants after a reaction. What do I mean by after a reaction? Only once it's reached equilibrium. Okay? So we can't just mix it and say, okay, 10 seconds, now it's after the reaction. No, it's once it's reached the point where we can evaluate the balance of products and reactants, i.e. equilibrium, that's when our equilibrium becomes valid. Okay? So it's kind of an odd thing to think about, but it's something you need to be aware of. Okay? So we could end up with this expression for A going to B, where equilibrium constant is going to be our concentration of our products over the concentration of our reactants. Okay? And yes, we can bring in all sorts of other orders and things like that that I don't want to deal with. The other way you can look at it, which is, I think, a little bit more scientifically rigorous, instead of just saying, well, it's the balance of products and reactants, we can go back to what equilibrium means. Equilibrium is in reference to the rate of the forward reaction being equal to the rate of the reverse. Okay? Kind of an interesting concept, because when we look at equilibrium, equilibrium is only concerned about our products and reactants. And ultimately, what about our products and reactants? Kind of a ratio, but what's going to determine our product versus our reactants? Ultimately, the energy. Equilibrium is all about thermodynamics. What's interesting about our other definition? Rate. What's special about rate? That's all about kinetics, the complete opposite of thermodynamics. So I think that definition is a little bit more interesting because it actually starts to attempt to bridge the gap between kinetics and thermodynamics. It ultimately doesn't do a very good job because you end up shifting from kinetics directly into thermodynamics. Okay, we don't have that smooth transition, but we end up with the same with the same general relationship, that our product energies are related to our reactant. Okay, through that ratio. Questions about that? Okay. So if we go back to water, we could look at water acting as an acid, or technically as a base. Typically we look at it as an acid. We could create the equilibrium expression, our products over our reactants. Okay? And we could find that our equilibrium constant is going to end up coming out to be 1.80 times 10 to the minus 16. Does that number look odd to anybody? Just curious. Okay, maybe we'll just leave that alone then. Typically, what do you think of when you think of the equilibrium constant for water? Go back to pHs. That's 7. 10 to the negative 7 is the concentration of hydrogen ion. But if you generate 10 to the negative 7 hydrogen ions, what did you generate for OH? 10 to the negative 7 as well. Put them together, and typically what most people remember, or should remember, 10 to the negative 14. Why is K here not 10 to the negative 14? What is K equal 10 to the negative 14? It's not the equilibrium constant for this reaction. No.
It's 15.7.
Which is your pKa, which we'll get to as well. There it is. It's your Kw. The Kw for water is H plus times OH minus. Where did water go from? Where did the concentration of H2O? In a standard solution, what happens to the concentration of water? Any reaction, what happens to the concentration of water? By how much? Very, very small amount. Water concentration stays relatively constant through any reaction that you run within water. Why has that become important? Well, then that means the concentration of water becomes a constant. Well, what did we say capital K was? A constant. So we can take the concentration of water, which is a constant, multiply it by other constant. We generate a new equilibrium constant, Kw. We use this Kw. When is this Kw true? At 25 degrees Celsius. It's not a completely dissociation. In fact, that's why your H plus and OH minus typically come out at 10.7 for neutral concentrations. So when we look at a reaction run at 25 degrees Celsius, this equation becomes true for any reaction occurring in water. So what happens when you add an acid to it? What happens to the concentration of H plus? It increases. Well, this equation must still hold true. So what happens to the concentration of OH minus? Decreases. Okay? So we can see that kind of balance between this, and that's what our Kw is trying to do. Okay? So we can play around with that a little bit. Okay? So as long as waters are solvent, we can go through and manipulate our Kw, and we can determine the amounts of acid and base present in our solution. So it's kind of a neat process, or a neat deal, if you want to look at it. We also introduced this other concept. That K is 1.8 times 10 to the minus 16. That's an awful lot of work to go through. As Carlos was suggesting, the other term for water that we might remember, we being the royal, not royal, I mean actually everybody, that you might remember for water is 15.7. What is that 15.7 number? It's the pKa for water. Okay, so we're still looking at it acting as an acid, but why do we refer to it as the pKa and not this 1.8 times 10 to the negative 16? It's easier to work with. Okay? The pKa is a logarithmic scale that ends up converting this exponent, okay, this big long multiplier, into a much more manageable number. Okay? The standard ranges that you might remember from organic chemistry, you're looking at probably 1 up to 50. Okay? Maybe 60 if you really want to push it. Okay? The lower the pKa, what does that mean? The more acidic, the stronger the acid. Right? What about the higher the pKa? The weaker the acid. It says nothing about the base strength. Be careful about that. Okay? That is a very common misconception. I've definitely made that mistake every so often. Okay? Your pKa is only looking at acid strength. So the bigger the number, the less acidic. Okay? That could mean more basic, but not necessarily. For example, pKa of an alkane, say CH4. Anybody remember the general pKa of your alkanes? 50 range. Okay. So if we run that logic with a pKa of 50, we would say, well, that's an extremely strong base. What does our base need to be able to do? Accept hydrogen ions. How does it accept hydrogen ions? It needs electrons. It has to have a pair of electrons. Does CH4 have a pair of electrons? No. Okay. So again, be careful with how you interpret those pKa's. Why is it important to go to pKa's? We get a number that makes it a little bit easier to deal with. Instead of stringing out a K of 1.8 times 10 to the negative 16 for water, I can actually say the pKa for water is 15.7. It's a little bit easier to work with, and if we shift into that scale, we can interpret things a little bit more quickly off of it. All right? So what happens if you have a pKa lower than 15.7? What does that mean? More acidic than water. If it's greater than 15.7, less acidic than water. Okay? So it allows us some quick ability to interpret. Okay? That P value, all that P means is we take the negative log of whatever comes after it. Where else have you seen this P scale? pKb, okay, fair enough. Kind of the inverse of our pKa. Say there's an easier one. pH. What's happening with pH? That was a way that we could represent the concentration of hydrogen ion in a solution. But we end up converting it, instead of being this crazy exponential number that most people would go glossy-eyed over, okay, we can now convert it to now a pH scale where we say pH is 2, pH is 1. Okay? Why do that? because we can now quickly interpret how much relative acid is in there. Okay, so if we have water, what's the concentration of H plus in neutral water? Okay, if it's neutral, what's the imbalance of H plus and OH minus? They're the same. So that means in neutral water, what's the pH? 7. What's the concentration of H plus? 10 to the negative 7. Okay? Moles of H plus per liter. So it allows us to get that kind of interpretation in it, and we don't have to deal with that 10 to the negative 7. Why is that also helpful for us? If our pH drops below 7, we now increase the concentration of H plus, decrease the concentration of OH minus. So it allows us to kind of see that balance. Okay? Everybody loved this section in 152, right? Yes. Really? I actually got legitimate yeses. That sounded a bit odd.
Once I got the logs down,
Okay. Most people tend to ignore and forget this, and we might very well swiftly end up doing that with this material as well. Okay. Why is it important in biochemistry? What's that? It's made up of water, so every reaction we're doing is being done in water. So this Kw does become important because all of our reactions are happening in water. Argue there's another important reason.
The pH will affect how a reaction takes place?
pH is going to change our reaction and take it a little bit away from that. pH is going to allow for an acid-base reaction to occur. Okay, well, why do we care if an acid-base reaction occurs?
Because what we use competes with water.
Water's concentration of H plus and OH minus is relatively weak, so we don't have to look at it competing with water. I forgot what my next slide was. Why does biology care? So it was the slide I thought it was, just in case you thought I didn't know what I was talking about. If we take a look at standard organic reaction, those of you that were ever in my organic chemistry labs probably recognize this. Why should we care about acid-base reactions? What changes in the course of this reaction as we go from left to right? The physical properties drastically change. We go from a molecule that is primarily, has an ionic interaction, which means we've got something that is a salt. What can we say about salts in water? They are highly soluble. So we look at a compound that dissolves in water. What happens when we do an acid-base reaction and put a hydrogen on it? I can kind of accept turning it into an alcohol. Why kind of? If we string that along with the carbonyl, we're looking at a carboxylic acid. So we got the hydroxy next to the carbonyl. Okay, what happens to the solubility now? Decreases to the point that actually we call this compound insoluble in water. Is the exchange of hydrogen ions a critical importance to biochemistry? Yeah. If we put a hydrogen ion on a molecule, we might very well take it from dissolving in water to now all of a sudden not being dissolved in water. Okay, well, if we look at our bloodstream, okay, our bloodstream, we've got things moving through it because everything's relatively fluid. Okay? What happens if all of a sudden a whole bunch of things don't dissolve in water or don't dissolve in the blood? You end up forming a clot. Everybody, well, you don't necessarily die, but you increase your likelihood. You prevent that blood flow. Okay? So this acid-base chemistry does become of really critical importance when we're looking at biochemistry. And we're really concerned about that balance. That balance is something that the body does a really good job of doing what with? Maintaining. We get that homeostasis. Why does the body want to maintain that blood pH or even cell pH? So we don't get this solidification aspect. We don't physically change, or we don't do a physical property change on those molecules. They are consistent. They always hold those same general trends. Okay? We do need to be able to vary. Why should it vary? We look at life. Does it constantly moving and changing? Yeah. So we do need some way to be able to reverse that process. Okay? So we want something relatively simple to go back and forth with. That's kind of our homeostasis. We're looking at that acid-base reaction playing a huge role in how these reactions can occur, or larger reactions can occur. Okay? So we end up looking at something known as buffers. Everybody's second favorite part of 152. Okay?
All the stuff I forgot.
Yeah, don't worry, I did too. So what to be honest, okay, what we're looking at is the Ka, that equilibrium constant, okay, for an individual acid and its balance between products and reactants. And what we further said was that that concentration of hydrogen ion, whether it's present or not, can have a drastic effect on the overall solution. So what we want to do is be able to monitor the concentration of hydrogen ions. So we could go through and try and rearrange this. Okay. And somebody thankfully went through and did that. Who rearranged it for us? Presumably Henderson and Hasselbach. I don't know if that's a legitimate hyphenated name or something else. And we can get the relationship between the pH and the pKa of our acid. Okay. Which then also tells us the balance of the conjugate base, our conjugate base being Ra minus. Why is it a base? In this case, we got a couple answers. Does it have a hydrogen? No, so it can't be an acid. Why is it the base? What do bases need to do? They need to accept hydrogens or donate electrons. What's the charge on A minus? Negative. It has those extra electrons. We're looking at a conjugate base. What about HA? HA will be our acid. Right? So biology goes through and picks a variety of buffers. Okay? Some compound with a particular pKa, and it uses that to stabilize the pH. How does it stabilize the pH? What happens if we add a bunch of acid? How does it minimize it from fluctuating? What does our acid have? It has the original acid and the conjugate base. So if I add H plus to this, what happens? An acid-base reaction between the conjugate base and the acid, getting rid of that excess H plus. Now I don't have to worry about that hydrogen ion because it's been absorbed by the buffer. Now it's not going to go in and mess with my reactions. Okay? What is that also going to do as far as the pH? Well, if it absorbs the hydrogen ions, how much is our pH going to change? Not a whole lot. Hence the buffer. Our buffer is kind of balancing that pH within a particular range. Okay? As I'm sure you guys all remember from 152, you can run a variety of reactions with these, ice charts, all sorts of other fun stuff with this. I know you all love it, so I figured we'd go ahead and work through one. Changed my mind, I don't really like ice charts either. So we aren't going to stress as much about that in biochemistry. The very last slide of this does have an ice chart showing up with it. We'll kind of leave ice charts to a more advanced biochemistry class. Okay. Where it's going to end up really showing up is if you moved into a biochemistry lab. Hint, anybody in the lab, we're going to have to make buffers. Okay. And we can, again, kind of dodge around this whole buffer issue and getting something to a particular pH by doing very simple kind of observational things. So in a lab environment, if we wanted to go through and, well, okay, I'm not quite there yet. So what I really want you to do is be able to interpret your pKa's. Okay? And I want you to be able to interpret that buffer range. So we'll look at some titration curves periodically. You need to be able to interpret those fairly quickly. Water is our 15.7. If it's smaller, it's more acidic. Bigger than that, it's less acidic. Doesn't say anything about the base strength. Okay? So then the next big question, it's kind of a fun one. What is the pH of a solution that contains an acid with a pKa of 4.6? Very common misconception. That's not the common misconception. Common misconception is the pH is 4.6. No. Okay. Our pH is dependent on the pKa and the balance of the conjugate base and the acid. Without that balance, if I just tell you the pKa, can you tell me the pH? No. Okay. So this question is unsolvable. Until we know more information about it, you can't do that interpretation. Okay? If you're told that it is in a buffering situation, then you could start to do some more interpretations. You're probably centered around that pKa. Okay? So how do we know we'd be centered around that pKa if you're in a buffering situation? Take a look at a titration curve. Should have picked an easier one to look at first, but this will work fine. We want to be able to do some interpretation from this. Okay, so to start off with, we have, sorry, my pen just spun on me. The acid, or sorry, do we know it's an acid? How do we know it's an acid? The pH is starting very, very low. So what we're looking at is taking HA, and what we're concerned about is its balance with hydrogen ion and its conjugate base. Okay, that's what we're kind of evaluating. What's happening in the course of this? We start adding sodium hydroxide. What does the sodium hydroxide react with? It's going to react with the H plus to form H2O. So what happens to the concentration of H plus? It decreases, which means what happens to the concentration of H plus up here? Sorry, I guess I should do up here in blue. That H plus concentration goes down, which means, is this arrow in between valid? No, because we're no longer at equilibrium. Reaction freaks out. Le Chatelier's principle says what happens? It pushes it forward to form more acid. Okay? Well, we just added base, which removed the acid, but then we put more acid in to replace it, or the system itself added more acid. So what happens to the pH? Relatively. Relatively, it's going to stay the same. There was acid present. We got rid of that. The system said, screw you, I'm going to put more acid back in. Okay? Because HA has the ability to release that acid into the solution. So theoretically, we get a flat line. The pH stays constant. What happens is I continue to add base. Eventually, we run out of HA. If I run out of HA, what happens to the concentration of H plus? Not only does it start to go down, it almost disappears. And what we end up seeing is now a spike in OH minus. So what happens to the pH at that point? It drastically goes up. And so what we end up seeing is these sharp increases in the slope of that line. At those points, our buffer system has been destroyed. We no longer have the ability to buffer, and that's why our pH jumps. All right? There's some other pieces of information that we can kind of pick out of this. So let's go ahead and take a look at some points here. What compound is present at the red dot down at 0?
Acid.
Can I be a little bit more specific?
H plus.
HA. Okay, yes, technically there's H plus there, but H plus could have come from anywhere. So we want to be a little bit more specific with what's present. We've got HA. As we add base, what happens? Okay, we start to lose HA. Okay, until eventually what happens? pH spikes. Why did the pH spike? Because HA was all gone. So what's present at that point, right where we get that spike? Okay, our HA concentration is 0. So what's left? Can't be hydrogen ions because our pH wouldn't have spiked. Our A minus is present. Okay. Notice that we continue to add base, and what happens? It levels off again. The only reason it would level off is because that OH minus is being removed somehow. Well, how can OH minus be removed? Remember, water doesn't generate enough H plus to do that. What was that, Scott? Kind of, what are you suggesting?
There's 2 hydrogens.
there has to be another source of hydrogen. What does that mean? Is this really HA? No, it's H2A. There are 2 acidic hydrogens in that compound, which means at our first point, we don't have our HA concentration equaling 0. We have H2A equal to 0. And what ion is actually present? Is it A minus? It's HA. Now as we continue to add base, it will eventually show up. There it goes. Okay. Now as we continue to add base, that hydrogen is removed and our pH again maintains a relatively flat line until eventually what happens? We completely remove it and we end up with, okay, now all A minus 2 because it lost 2 hydrogens. Okay. Last thing I want to get at here, we'll come back to this tomorrow. I just have to realize we're done, and apparently the other class isn't pushing in on us. Maybe they got tired of waiting. What happens when A minus equals HA? Log of base over acid, if the concentrations are the same, any number, pick a number. 1. The concentration of A minus is 1. What is the concentration of HA? 1. What is 1 over 1? 1. What's the log of 1? 0. So at the point where my conjugate base equals my acid, what can I say about the pH? It's equal to the pKa. When does that point occur? At the inflection point, so let's adjust this for you guys here. Let's take a look at our first one. If we say it's at the inflection point, what's the concentration of H2A? 0. What's the concentration of HA? All of whatever we started with. Are they equal to each other? No. Where are they equal to each other? At the half equivalence point. So we take half of that volume, and I'm going to approximate, I think that's half. At that point, the concentration of my H2A, it's just I'm bringing back nightmares. That's always good. Our HA minus, and at that point we know that the pKa equals the pH. So we can now interpret off our titration curve some information about our acid. We now know that the pKa for that first acid is roughly 2. I counted that right? We're looking at roughly a pKa of 2. Okay? Kind of gets us some information. Okay? Sorry, I definitely talked too much. So we'll go ahead and stop that there. We will pick